participants, resource persons, and teacher participants who are from different universities who are gathered here through online mode for this occasion of Pi Day, that is 14th March, a program organized by Department of Mathematics, a popular talk on how to cut an Uttapam to get the desired number of pieces. So for this talk, we have the resource person, Dr. Priyavrat Deshpande from Chennai Mathematical Institute.
Dr. Nishank Pimpळे.
Yes, sir. Yes, sir.
मुत्ते पवार सर जॉईन झालेले आहेत का?
Yes, sir. Yes, sir. Mutte Pawar sir is also joined.
हो सर.
Yeah.
जॉईन झालेले असतील तर देशपांडे सरांच्या अगोदर त्यांना 2 मिनिटं देता का? शुभेच्छा देतील त्यांनी.
Yes, sir. Definitely.
बोलता का?
Yes. I welcome our former principal, Dr. S.M. Mutte Pawar sir, for this guest talk. So, and for this today's program, we have the chairperson, Professor S.N. Shinde sir, and the resource persons, we have Dr. Priyavrat Deshpande. So first of all, I request our former principal, Dr. S.M. Mutte Pawar sir, to say a few words about this 14 March occasion.
वावरे सरांना प्रस्तावना करू द्या ना.
Okay. So before that, I request head of the Department of Mathematics, Dr. Mahesh Vaure sir, to give introductory speech and the introduction of today's resource person.
Thank you, Nishank sir. Good morning to one and all. Today we are celebrating Pi Day. On this occasion, for this program, the chairperson of the program and vice principal of our college, Professor Sadashiv Shinde sir, one special invitee who is former principal and former head of the Department of Mathematics, Dr. S.M. Mutte Pawar sir, today's resource person and my classmate, Dr. Priyavrat Deshpande sir, Chennai Mathematical Institute, Chennai. My colleagues, Ashwini Kare, Deepak Guge, and dear all participants. First of all, I'll wish you all, everyone happy Pi Day today. This pi is a irrational number, and at present, the pi has calculated out of 31.4 trillion digits. Its approximate value 3.14 will be celebrated as per the American date. The 3 stands for March and 14 stands for the today's date. So 3.14 will be celebrated this Pi Day from firstly from the physicist Laurie Shaw in 1988. This pi was first developed by used by William Jones during the year 1706, and later on in 18th century, the Lambert proved that this pi number is irrational number. Although it is irrational, but it has various uses in all the field of science, as well as mathematics also. German mathematician that Lindemann also proved that this pi is the transcendental number. So on the occasion of this, we have decided to organize a popular talk by Dr. Priyavrat Deshpande, who is going to give on how to cut an Uttapa. Uttapa is also one circle to get desired number of pieces. With this talk, definitely participants will be happy today. I'm going to introduce today's resource person now, Dr. Priyavrat Deshpande, who has done his MSc from Pune University during 2002. Later on, he did his PhD in 2011 in mathematics from University of Western Ontario, Canada, under the supervision of Graham Denham and Jan Minek. He completed his postdoc from Chennai Mathematical Institute, and his interested area is topological robotics, application of algebraic topology. At present, he works as placement coordinator in Chennai Mathematical Institute, Chennai. He also coordinates the Madhava mathematics competition. In that, he has published his 6 research paper and 4 are in pre-printing. Recently, 2 years back, he received the SERB matrix for 3 years. It is from June 2018 to now. At this month, the grant will be end at March 21. Under his guidance, one postdoc students and at present one research student is also actively working. And he also runs the activity of the math cell along with his wife. She is also working at Chennai Mathematical Institute in the field of mathematics, named Kavita Sutar. This is about introduction of Dr. Priyavrat Deshpande. Another special invitee, Dr. Subhash Mutipur sir. He is ex-principal of our college, and he is head of the former head of the Department of Mathematics of our institute. I also welcome him here. Thank you, one and all.
Thank you, sir.
Impress, sir, carry on.
Yes, yes. Thank you, sir. So once again, I welcome all the participants for this popular talk on the occasion of Pi Day. I wish all of you happy Pi Day. Now I request our former principal and head of the Department of Mathematics, Dr. S.M. Muttapam sir, to say a few words about this on this occasion. Please, sir.
Thank you, Nishank.
Yes, sir. Thank you, sir.
Am I audible?
Yes, sir. Yes, sir. You are audible, sir. Please.
Okay.
Yeah.
Okay.
Yes, sir.
Okay.
Yes, sir.
Thank you. Thank you. Thank you. The chairperson of the talk, my friend, the vice principal of the college, Mr. Sadashiv Shinde, all the colleagues. I have immense pleasure to talk with you on the occasion Pi Day that is being celebrated by my college, Rajarshi Shahu Mahavidyalaya, Latur. The speaker, Dr. Priyavrat Deshpande, had chosen very nice topic. Though the problem belongs to the combinatorial mathematics, has been transformed to other branches like algebraic topology too. And many of the researchers, leading researchers in the world, are working over this problem nowadays. It's a very nice opportunity that the students of this area are getting exposed to this subject. It's very interesting. The title of the talk itself tells you that something must be interesting. And from this day-to-day problem, how that problem is taken over to the mathematical field, that you can experience yourself from this talk. I extend my best wishes for such an effort arranged by the Department of Mathematics and by the college. Thank you all. Okay, take over, Nishank. Nishank, please take over.
Nishank,
Yeah, thank you. Thank you, sir.
Nishank.
Yeah.
Take over. Okay.
Thank you, sir. Thank you, sir, for your precious talk. Now, I request today's resource person to deliver his talk. Please, Dr. Priyavrat Deshpande, sir. Will you please share your screen?
सगळ्यात आधी धन्यवाद माझे मित्र महेश, प्राध्यापक महेश वावरे आणि सगळे प्राध्यापक शाहू महाराज कॉलेजचे आणि गणित विभागातले सहकारी सगळ्यांना तामिळनाडूमधून वणक्कम. ओके, एकच Right. So my plan for today's talk is to have a very interactive session. So I expect that there will be some amount of interaction, and I don't plan to teach anything. Instead, I want everybody to experience this journey of discovering mathematical ideas. And we don't have enough time for this, but I'll try my best to give you some exposure or some experience of mathematical discovery in next, say, 55 to 60 minutes, approximately an hour. And I would welcome if there are any questions. So please do not hesitate. You can just stop me anytime in between, and then we can have a discussion, and I'll move forward. There is also no restriction on the language. मला अगदी व्यवस्थित मराठी बोलता येतं, त्यामुळे कुणालाही कसलीही अडचण वाटली किंवा प्रश्न वाटला, सांगता नाही वाटलं, तर आपण कुठल्याही भाषेचा वापर करून, म्हणजे मराठी, इंग्रजी किंवा हिंदी, तमिळ मला समजतं, फक्त बोलता येत नाही. तर अडचण होते बोलायला, अजून एवढं पक्क झालेलं नाहीये. पण ह्या कुठल्याही भाषेमधनं आपण आज संवाद साधू शकतो. पण प्रामुख्याने मी इंग्रजीचा वापर करेन लिहिताना. तर मी सो नाव I will share my screen, switch off my video, and I'm going to write. I don't plan to present slides. Okay, so let me just switch off my camera and let me share my screen. Okay, start broadcast. Okay. Right. So I hope this is visible. So the title of the talk, if I remember correctly, is how to cut an Uttapam to get the maximum or desired number of pieces, right? So slightly catchy title, but I would like to disappoint all of you. There is no Uttapam today. There is not even a picture of any food item in the talk today. But what you see in front of you right now is something called as an arrangement of lines. So 47 lines are drawn on the plane, and in such a way that it breaks the plane into triangular pieces, right? If you look at all the pieces formed, or this pattern formed by drawing these lines, you'll see that each of this is a triangle. Okay? And even so, these are bounded. If you think of this region, so these are unbounded region. So unbounded region is also triangular in the sense that if I were to draw a circle at infinity here, that will serve as the third side of the triangle. So this is called as a simplicial arrangement of line. Okay? So that is all about this title. But let me move on. So quickly, let me write down the plan of the talk. So what I plan to cover, so that all of us will have an idea as to whether I'm progressing on the right path or no. So first, I want to say a few words, or basically I want to understand from the audience what they think how the mathematics is done. So I want to spend maybe 5 or 6 minutes interacting with the audience in order to get the answer for this question, how the math is done. I'll explain the question later. Then I want to talk about something called as the inductive attitude. So this will also be a short discussion. And then I want to turn to the actual math part of the talk, which is the partitioning problem. And its solution. And then finally, if there is time left, we can talk about some other related problems, or this may even seep into the third portion of the talk, right? And the theme of today's interaction is, let us guess, let us experiment. Okay. So if you have been doing mathematics for at least more than 5 years, they should probably come to you as a surprise. So let me begin with this question: how math is done, right? So let's try to understand. I would like to ask this question. So all of you must have learned mathematics at the school level, at 11th, 12th level, and then later on in your undergraduate studies. So how do you, so can you give me one or two words when you look at mathematics and other subjects, which include other scientific subjects with very strong experimentation flavor, and also subjects from the humanities background? So how does mathematics compare with those other subjects? As a student, as learning goes, how do you compare mathematics, right? So let me write down here some peculiarities about mathematics, right? So in order to start, so usually I do this talk in front of the audience so that I can see, read the faces and actively interact, but this is an unusual mode for unusual times. So I have really no idea how everybody's thinking at this moment, but to give you an idea, let me give one of my answers to the question that I've posed. So I think mathematics has very rigid standards. So when I compare mathematics with, say, history or even other scientific subjects like biology, I feel that mathematics has very rigid standards. Everything is laid out for me. I feel that sometimes I feel that there is nothing much I can do on my own. So this is probably one way mathematics is different from other subjects. So I would like participants to say what their experiences. Please, anybody?
Participants are requested to unmute and talk, interact with the research person.
So there is no right and wrong answer here. I just want to understand what people think and what people feel about it. So please go ahead and share.
Yeah.
Mathematics is precise.
Okay, it's precise. So I'll say precision. Right. Anything else?
It deals with the logic of shape.
Right. Yeah, okay. So maybe I'll just add one more adjective and say that mathematics is clarified by logic. Excellent. Is there anything else anybody wants to add?
Imagination.
So do you want to sort of expand on that? What do you mean by imagination?
Things which do not visible, but we imagine this in mathematics.
Okay. So maybe I will, yeah, okay, I understand your point. So I'll write imagination.
Sir, curiosity.
So what? Curiosity. Okay. So curious. So how does curiosity is a characteristic of mathematics? Can you say? Because curiosity is probably associated with a person, but why is math curious? Math is curious.
to understand the questions about what's have in the questions to clear of this conditions
Okay.
of these questions.
Okay. Your point is that when you study mathematics, curiosity is an important aspect, right? So curiosity,
Yes.
okay, fine. So it is not really about math, but if you want to do math, curiosity is an important factor, right?
Yes.
Okay. 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 Anybody else want to pitch in? Right. So I will just add abstraction to imagination. So for example, even in experimental physics, we don't go beyond what we don't perceive, right? So, but in mathematics, you can talk about some 18-dimensional manifolds and write a paper about it or whatever. And you can talk about 1,000-dimensional vector space, and that you need not perceive it. You cannot see it, you cannot smell it, you cannot hear it, but that's fine. You can still do mathematics with it, right? So that's one peculiar property of mathematics, right? Anything else anybody wants to add?
One is required to solve the problem in a specified structure.
Right. Okay. So let me just, if I may, I will write it as codified, right? So there is a strict code in mathematics, right? Or a specific way of expressing yourself. So it could be about writing a paper, writing a solution to a problem in the textbook, or generally expressing yourself in mathematics. You have to be very specific. You have to follow a certain code, which may not be in other subjects.
So condition is also
Sorry, what do you mean by that?
condition. In
So
mathematics, questions have many conditions.
okay. So can you explain it with an example so it will be clear to me?
So if you want to assume something and then with that condition one can prove like that.
Okay, so then I will still add it to this sort of codified or specific way of expressing yourself in mathematics. I'll still add to that. So that's how. So there is a way of sort of, yeah. So I'll add it to this. Anything? I mean, I think we've gathered enough material. Yes, please.
In a mathematics, you can able to see any situation by so many angles.
Okay, so maybe I'll say wider perspectives. So the perspectives that you can bring in are basically limited by our own limitations, right? There is, so we don't have to limit ourselves by what we see or what we perceive. We can just go beyond that. So that I will also connect this to imagination, if I may. Right? So it offers really wide perspective. Yes, very true. It's probably like philosophy or of that nature, that even if you don't see something, don't perceive something, you can think about it, and you can talk about it, and you can develop theory about things that you don't see or that don't exist beyond your imagination. Very true. Okay. So, I mean, there is a lot one can say about this, and this in itself is an interesting topic to discuss. But let me leave at that, and let me move on. Right. So, I'm going to make a statement. So the mathematics that we learn in school, high schools, colleges, or even universities, when there is a textbook involved or a specific subject involved, we follow this method of what I would like to call it as demonstrative reasoning. So let me, instead of defining what I mean by demonstrative reasoning, let me tell you what it doesn't mean, right? And we'll start from there. So for example, let's say you are in a court and a lawyer is presenting some circumstantial evidence and trying to build their arguments based on the circumstantial evidence. So something like this does not fly in mathematics, right? Because you have to demonstrate what you're doing, and that has to be the ultimate truth. It cannot be that 2 plus 2 is 4 only in 21st century. In 22nd century, it will change, and 2 plus 2 will be something else. Or 4 times 6 is 12 on Earth, but if you go to Jupiter, it gives different results, right? Something like this may happen with some physical phenomena or biological phenomena, right? That this is true only on Earth, but you move to a different planet, and which is also true for physics, that certain things are true only because you are in a certain situation. But you go to a different planet, you go to a different system, you go to space, outer space, and things change. And whatever you have said is no longer true. But something like this will never happen in mathematics. Whatever was proved that this and this is true, Pythagorean theorem, right, which was probably should be attributed even before Pythagoras to Baudhayan. But whatever was proved, say whatever 3,000, 4,000 years ago, to date is still true. You go to any planet or any sort of cosmic body in the entire universe, that theorem is still going to hold true, right? So this is what I mean. So this sort of rigid thing is mathematics, right? So demonstrative reasoning, whatever it might be, I've not really defined it, but I would like to say that it is safe, right? It is, what I mean by that is it's beyond controversy. Once you prove something, once you establish it, it's established. There is no controversy, and in that sense, it's final, right? So these are some of the characteristics of demonstrative reasoning, and that's how we learn mathematics, right? Because we've been taught that, okay, first of all, you have to believe that certain axioms are true or they hold. Based on that, here is your first definition. Based on these first definitions, here is your first lemma, and based on these lemmas, here is a theorem, and that's how a theory progresses. That's how Euclidean geometry sort of evolves. But the problem with demonstrative reasoning is that it is incapable of yielding new knowledge. Okay, so let me actually make that a point. So demonstrative reasoning is usually incapable of yielding new knowledge. Right? See, it sounds good that there is no controversy, right? But if there is no controversy, then how are you going to challenge something? Right? So that's what sort of makes physics or other experimental sciences very different from mathematics, right? So, I mean, I already said inductive evidence of a physicist, or circumstantial evidence of a lawyer, or a documentary evidence of a historian, statistical evidence of an economist. So this is something, even though those things are not codified by logic, there is nothing, there might not be strong foundation, but because of this, people are sort of compelled to find something new, discover something new, come up with new theories, invent new gadgets, right? So this is something which is lacking in everyday mathematics, right? So this is, I mean, my personal experience. If you want to sort of contradict it, I'm open to have a discussion. So my question is, how do we implement this in mathematics, right? So how many of you have learned mathematics using experiments? Does anybody want to share their experience with learning mathematics in a different way? The way one would learn physics or other experimental sciences or humanities. Is it possible to learn mathematics like that? That you have been not told of any theory, there is no foundation that has been laid out for you, but you go out in open and start learning mathematics by doing experiments. Is that even possible? How would you, if you had no idea, how would you figure out and how would you convince yourself that 2 plus 2 is 4? What is 2 plus 2? What is the process of addition? And how would you say that this is 4 and not 5? If you were not told that this is something which is a truth, or if you had no idea that something like this could. So how would you go about this? Any suggestions from the audience, or sort of anything that comes to your mind that you want to share? Maybe I'll wait for a minute and then. So.
Yes, sir. With
Yes,
the examples
go
of
ahead.
chocolates.
Okay. But don't you think those examples are sort of synthetically tailor-made so that you get a perception that you are really understanding something, but not really going to the roots of? See, can you imagine, say, some prehistoric humans who really needed math and they had absolutely no background for it?
Yeah, they use lines now. 2 lines,
Yes.
2 plus 2 lines is equal to 4 lines.
Yes, but that is a tool. But how did this urge for addition came in, and how would they would have understood that, okay, this process should be done like this?
Yeah, that that I can't tell. How
Okay.
they know this is called as addition only? You are asking the same, na?
Yeah, similar. Yes. I mean, I'm not really stuck up on addition. I'm just trying to understand how would you learn mathematics by experimentation or implement the inductive attitude.
Uh, I can tell you about the fractions. In primary school, we learn fraction by the cutting the rotis or a pizza,
Right.
like that.
Okay. Okay.
If we cut the pizza in 4 parts, then
Okay.
one of it is called as 1/4.
Right.
One part
Yes.
is like,
Yes.
yeah.
Yes. Right. But that experimentation, do you do in your BSc?
No,
I
not in
mean, of
BSc.
course, I wouldn't say fractions because that is something that you've already picked up. But yes, so my point is exactly that. So this sort of methodology of experimentation or sort of demonstrative methodology, can you implement it in a BSc classroom?
No.
Suppose you want to learn, say, combinatorics, calculus, or whatever, several variable calculus, linear algebra. Can you implement the similar, or say, abstract algebra? Can you implement a similar methodology to learn? Okay. So I'm
Give me
actually
some time,
asking
sir.
pretty hard questions, and sorry to interrupt because I also have to keep an eye on the time that we have. Right. So there is one way of doing it. I'm not saying that it's the only way of doing it. So I'll just write down a few pointers, and then we will actually see this in action. So first step is observation and pattern recognition. Second is conjecture formulation. Third is experimental evidence. And fourth is the proof. Sorry, so I needed the here. The proof, right? So I'm pretty sure if you say learned the rank nullity theorem or I don't know this. Not sure what the syllabus is currently, but you say first isomorphism theorem in group theory or Silo theorems or whatever. I'm not very sure, but whatever favorite theorem or whatever least favorite theorem that you can think of, can you frame? I mean, can you say that you learned it using these four steps, right? And I'm pretty sure the answer is no, because that's not right. So in the remaining 20-25 minutes, or let's say half an hour, I'll try to demonstrate that you can learn mathematics using these four methods. So I'm not sure we could actually we'll be able to write down a formal proof at the end, because we don't really have enough time. But I'll at least tell you that I'll give you a feeling that there is a proof, and if you sit down, you'll be able to write it down. Okay. So for that, I've chosen something which is usually not in any college syllabus, so that it's completely new. And so let me phrase the problem for today. And at the end, in the discussion, I'll be happy to talk about the inductive attitude. But I think I hope I didn't end up boring a lot of people. Right? So here is a question. Purely, so the math part of the talk now starts. So here is a question. What is the maximum number of parts formed by removing n straight lines from the plane? I'm hoping that this is not something that you've come across. Otherwise, if you know the answer, then there is no fun, right? So if you want, if this is new for a lot of you, let me just give you an intuitive idea of what I'm talking about. So assume that this blue thing is your plane R2, the Euclidean plane, XY coordinates, and suppose there is this straight line L, right? Now the straight line has equation AX plus BY equal to C for some ABC, not all simultaneously 0, right? So if I remove this, right? So basically from R2, I'm removing all those points X, Y, which satisfy this equation. I am left with points AX plus BY strictly greater than C and AX plus BY strictly less than C, right? So these are the two portions. And if this line, the points on this line are not present in R2, then there is no way you can draw, if you choose one point in which has less than C, other point which is greater than C, then there is no way you can join these 2 points by a path, because any such path will cross this line, but this line is now no longer in your set. It has been removed, right? So when you remove one line, the plane gets separated into 2 pieces, right? Now my question is, what if I remove lines, right? What is the maximum number of parts that I'm going to get, right? So this is sort of, ties back to that catchy title, How to Cut an Uttapam. Uttapam because I like South India, everybody eats Uttapam here. In fact, I had Uttapam in the morning. Right. So if I were to, apply straight cuts, I know then how many pieces I would get. And obviously the answer is it depends on how I cut, but is there a maximum? Is there a maximum, right? So let's start tabulating. And at this point, I would like the audience to participate. So here is a thing. Suppose I remove number of lines removed and number of parts obtained. Suppose I remove one line. Okay. How many parts do I get?
2.
Excellent. Suppose I remove 2 lines. How many parts?
4.
Right. So that's a maximum, but let's try to get all possible parts. So if I remove 2 straight lines, 2 parallel lines. So let me draw the lines of the blue. Then I get 1, 2, 3, right? 3 parts. And if I remove lines like this, I get 1, 2, 3, 4, right? So 3 parts, 4 parts. Maximum is 4. So the maximum number of parts is 4, right? So 3 lines. Anybody? What are the possible number of parts? I hope people have some writing material so that they can sort of scribble and try.
6.
And I'm going to
Four
if
and
you're
4. 6 and
6.
okay. So somebody
6,
said
7.
4. Okay. So somebody said 4. Somebody said 6. Somebody said 7. Okay. 5. Nobody said 5. 8. Nobody has said 8. I'll probably give you maybe half a minute to think. Then, yes, somebody said 5. Did you say 5? Did somebody said 8? Okay, why okay, why am I just talking? Let's do it, right? So how do you get, let's say 4 is the least. So how do you get four parts? By removing 3 lines. How do I remove lines? Can anybody tell me how do I remove lines in order to get 4 parts?
Straight line.
Sorry?
Parallel.
Parallel line.
1, 2, 3, right? L1, L2, L3. So I get 4 pieces. 1, 2, 3, 4. Excellent. And see, here is a subtle thing. If you're paying attention, so it doesn't matter what the actual equations of the lines are, right? Because there are like infinitely many ways to draw, say, 3 lines in plane. But as long as 3 are parallel, they'll always give you 4 pieces, right? And we are not really interested in the actual equations or the actual parts. We are just interested in the number. So as long as there are 3 parallel lines, I get 4. Okay. How do I get 6?
2 parallel, 1 horizontal.
Okay, 2 parallel and the other one parallel. So 1, 2, 3, 4, 4, 5, 6. Okay. Is there another way of getting 6 parts? 6 pieces?
3 concurrent lines.
3 concurrent lines. Excellent. So I get 1, 2, 3, 4, 5, 6. Right? And see, these are essentially different. Correct? Because here you see there are 2 points where 2 lines are intersecting. Here there is only one line where one point where 3 lines are intersecting, and here there are no intersections, right? How do I get 7 parts? So somebody said 7. So they should tell us how to get 7 parts.
Yes, sir. First 2 line cross itself.
Okay.
And third line is cross these 2 lines. We get
okay. So what
7
do you,
parts.
yes. So what do you mean is that no 2 are parallel, no 3 are and 3 are not concurrent, correct?
Yes.
Yeah. Okay. So I'll draw like this and this, correct? So let's count. 1, 2, 3, 4, 5, 6, 7. Awesome. Excellent. Very good. Right. So here there are 3 intersection points where exactly 2 lines meet, right? There are no parallel lines. There are no 3 are concurrent. Correct? In fact, there are only 3 lines. So, right. How do I get 5 parts? How do I get 5 portions? Is there a way to draw this thing, or is 8 possible? Can anybody give a sort of intuitive justification as to 7 is the maximum and it's not possible to draw 8 lines, 3 lines so that you get 8 parts? Sorry, excuse me. Think. Sorry, that's not much time probably. But anyway, I'm willing to wait because I think that's something. If you're sort of bored or you want to move on, I'm going to talk about 4 lines. So if you're sort of excited, just start working on 4 lines because we are going to talk about it. No? Yeah. So let's say that 8 is impossible. I mean, 7 is the max. But do you guys find a justification? How do I justify that 8 parts is impossible? Getting 8 parts is an impossibility. Or where is 5, right? Where is 5? Why is it that I try to cut, I'm trying to cut a piece of cloth using 3 straight lines and I'm unable to get 5 pieces. Why is that, right? Okay, so this is something I want people to think, and maybe later, if you get answer, we will discuss. Okay, next, 4 lines. Number of lines, 4. Number of parts, all possible. Let's just list all possible parts that when you remove 4 straight lines, you get, okay? So what is the minimum number of parts one can get if you remove 4 lines? Anyone?
8.
Is that the minimum? I mean, I will write it. I totally agree.
5.
4.
5.
Minimum.
Minimum is 4 or 5?
5.
5. Okay.
Minimum
8.
number.
Okay.
9.
Okay. Somebody said 9.
13.
Answer.
13. Looks like back.
Same.
Somebody said 10. Sorry, I missed what the number after 10?
4.
Oh, you got 4 parts? Very interesting. I'm going to hold you to that and ask you to explain how you got 4 parts.
Minimum parts will be 5 parts.
Okay, okay. But somebody got 4, so we should respect that. I'm not. Anyway, 11, 12. Did anybody get 11 or 12 parts by drawing 4 lines?
No. It may be possible that
Yes. Okay, so there are question marks right here, 6, 7, 11, 12. Okay, so the person who said 4, tell me how do I draw 4 lines to get 4 parts, please.
Parallel. 4-line
4
parallel.
parallel lines. 1, 2, 3, 4. Let's count the pieces. This is first, second, third, fourth, and fifth. There are 4 pieces. How do you get 4 pieces? Or do you want to change your answer? Okay, 8. How do I get 8? Can anybody tell me how to get 8 pieces? By drawing 4 lines? Yes?
Three parallel lines and one intersected line. Two.
Okay. Yeah, I understand. Yes. 1, 2, 3.
And intersected line.
Yes. One is the last one is not parallel. So 1, 2, 3, 4, 5, 6, 7, 8. Last one. Is there another way to cut so that you get 8 pieces? Right? Sorry, the drawing is really bad. Let me try again. 1, 2, 3, 4. Right? Sorry. Really sorry. 1, 2, 3, 4, 5, 6, 7, 8. Right? 4 concurrent lines will also give you 8 pieces. How about 9? How do I get 9?
Two parallel, two horizontal.
Yes, I agree. So if somebody were to draw this gives you 9. Yes, so this is 9 parts. I agree. 10.
Two congruent, two parallel.
Sorry, I missed it.
Two congruent, two parallel.
Yeah, okay. So 2 concurrent lines and 2 parallel lines. Right. And something like this, right? I mean, assume that this is parallel. I'm really sorry. Drawing is bad. Yeah, so I think this is 10 parts. Am I right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 10 parts. How do you get 13 parts?
Sir, first,
13.
Sir, first cross 2 line itself. Then draw at intersection 1 straight line.
Sorry, I missed it. I didn't hear what he said.
Okay, sir. First cross 2 line itself.
Okay.
Yes, and again one point of this intersection draw straight line. Means
from here?
Yes, 3 line intersect at one point. Means draw one line also. Yes.
Okay.
And draw horizontal 2 lines above intersection. One there and below one.
Oh, but we have only 4 lines, man.
Yeah. Okay.
We have to work with only 4 lines, not 5.
Okay, sir. Sorry.
No issues. No problem. So how do I get 10 is done? Oh, so that's how you got 13, is it? So 5 lines, 13 pieces. Okay, I understand. Okay. So what is the maximum? Is that the maximum? This 10 parts, is it the maximum? How about this? Okay, this is going to be tricky because my hand usually shakes and I forgot how to get a ruler. And let's see what happens here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, 11 parts. And my claim is that this is the maximum. Okay. Maximum. 13 is not possible. So let me erase 4, which is not possible. Let me erase 13 and 11. What about 6 and 7? Just like here 5 was missing, 6 and 7 here are missing. 2 possibilities are missing. They're not accounted. Yes.
By joining 2 crosses means.
How do you get 6? What do you mean by joining? No, but oh, like this, you mean?
Oh, no, sir, no.
Then, anyway, that's not.
Multiplication symbol.
Okay.
Symbol of
So I draw like this.
Then join them, sir, by another symbol.
Oh, you mean like this?
Yes, sir.
But see, it'll go. These are infinite lines, right?
Yes.
Right. So what do you get here? I think you got the same thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the same thing as this. These are infinite lines. You cannot just do like this. Okay. These are infinite lines. Very good. Yeah. Okay. Okay. So let me retabulate our findings. So now here, number of lines and maximum number of maximum parts. Right. So if I draw one line, I'll get maximum 2. If I draw 2, maximum 4. If I draw 3, maximum 7. If I draw 4, maximum 11. If I draw 5, what should be the answer? So did you just realize that we did an experiment here? I'm pretty sure something like this you wouldn't do in class. You would sort of present some lemmas and proofs and whatever propositions and state a theorem that maximum number of parts obtained by removing n lines is blah, blah, blah. Here is the proof. Okay. So what should be the maximum number of parts when you draw 5 lines? Yes, please.
16.
Why? Did you draw? Do you want to show us?
14.
14. Okay. Okay. So here is controversy, right? This is what I was looking for. 14 and 16. Which is true?
16.
16. So 2 votes for 16, 1 vote for 14. So who else wants to vote for 14?
16, sir.
3. Okay. 16s are winning.
16.
4.
16, sir.
16. Oh, so there are a lot of people saying 16. So who wants to support 14? And why 16? Why 16? To give me an answer. Yes. Yes.
So from line 1, maximum points 2. Then
Yes.
for finding of line 2, we add, then we got maximum number of line of 2 is equals to 4.
Okay.
And obviously from line maximum number of line 2, that add plus 3, then we get 7. Therefore 7 plus 4 is equals to 11, line 4 la. And line 5 la, the above sequence, from above sequence we add plus 5, there are 16.
Okay.
Number of line is 16.
But what you just said, is that a proof?
एक दोन तीन चार पाच सहा सात आठ नऊ दहा अकरा बारा तेरा चौदा. Hello sir. When we are drawing 3 concurrent lines and 2 horizontal lines to when we draw 3 concurrent lines, yes sir, yes, I say not this like sir.
Okay.
One cross multiplication cross symbol.
Okay, sir.
Then one cross straight line, vertical line between them. No, center from center.
Okay. Okay. Sorry.
And one horizontal line from upper side, 3 upper, and one from below, horizontal line. Then we get 14 pieces.
Okay. But my question is, I agree, but why is the 16 maximum? So I never said that you don't get 14. I said, what is the maximum number of pieces possible when you remove 5 lines?
Okay, sir.
So 16, I'm saying that this is the right answer, but why is this the right answer? So what about when I cut the plane using 6 lines? How many pieces maximum pieces should be possible? See, I mean, we should not forget the strong codified nature of mathematics, that there should be a proof which is backed up by well-established logic, right? I mean, this is not really logic, right? 2 plus 2, 4, 4 plus 3, 7, 7 plus 4, 1, 11. So this is just a pattern, but how do you actually prove that this pattern will continue? Okay, is there anybody who drew 5 lines to get 16 pieces? Yes. No? Okay, so let me not spend more time, because probably not sure. Did people get bored, or I don't know. So let you sketch of the proof, or it'll be actually the proof. See, first of all, observe that parallel lines imply fewer cuts, right? I have not started the proof yet, but I just want you to observe. So if you have parallel lines, then you're not cutting enough pieces. And if you are, you know, 3 or more concurrent lines, this implies that you're wasting a cut. Correct? I'll give you an example. Suppose I already had 2 concurrent lines, right? And I draw third concurrent line. So I pass through an intersection point which was already there. So if there is no intersection point, no new intersection point, I'm just wasting my cut. But look at here. If I don't draw third line concurrent, then I end up introducing new intersections. And the new, see, in this case, compared to the original figure that I had, 1, 2, 3, 4, I was able to cut only the first region and the third region, correct? With this line, only first and third were split into 2 parts. So that's how I get 4 plus 2. But if I draw this, then I cut first, second, and fourth. So I cut 3 pieces. Here I cut only 2 pieces. Here I cut 3 pieces. So if you pass through an already existing intersection point, you end up cutting, you end up wasting that cut because you're not splitting more regions. But if you introduce new intersection points, you end up cutting or you end up splitting more parts, right? So now if I were to draw, let's start again from here. So let's say this is my original figure, right? So 3 lines. So this is, say, region number, sorry, 1, 2, 3, 4, 5, 6, and this is 7, right? So now if I draw a line from here or here or here, I cut only 2 or maximum 3 regions, right? No, I actually cut only 2 regions if I go through this. But if I draw a line, let's say like this, where should I draw it? Let's say I draw it like this. So then I cut region number 6, I cut region number 1, region number 2, and region number 3. Right? So I ended up adding 4 more regions. And that's the maximum. Okay, that is the maximum. So the proof, I mean, I don't have the appropriate vocabulary right now, but the proof sort of goes like this. So we can use sort of induction argument. So let me just sort of, since I don't have enough time, let me just sketch it. Let Pn be the maximum number of pieces obtained by removing n lines, right? So now when I draw n plus first line, right? So what I want is that it should intersect. So it should be, so sorry, actually, I should say it should not be, first of all, parallel to any previous line. Okay. Second, it should not pass through an already existing intersection, right? So it shouldn't pass through an intersection point which was already there, which basically implies that the last line added intersects all the previous lines, which means that it cuts exactly n regions, n+1 regions into 2. So this tells us that Pn+1 is equal to Pn plus n+1. And that's what the sequence is. So this is P4, right? So this is P4. So P5 is P4 plus 5. Then P6 is P5 plus 6, and so on. And so on. And we already know that P1 is equal to 2, right? P1 is equal to 2. This is something we can establish, and this is the recurrence relation. Once you solve this, you'll actually get a formula for Pn in terms of n, which I leave it up to you to figure out. So let me sort of wrap up. I hope you are paying attention, and I sort of demonstrated the steps that I said earlier, right? So here are some questions for you to think. So number of lines, number of minimum parts, maximum parts, right? So when you draw just one line, you get 2. Doesn't matter, it's same. 2. This is 3. This is 4. 3, 4, 7, 4, 5, 11, 5, 6, 16, and so on, right? So this is for n, this is n+1, and this is actually, I'll tell you the answer, 1 plus n plus n, choose 2. This is the answer here. So my question is, for example, can you, so there is this gap, right? So minimum is n+1, maximum is 1 plus n plus n, choose 2. So can you draw lines so that you will realize the parts in between? For example, we drew, sorry, this was not, we drew 3 lines so that we got 6 parts, but 5 was missing, right? 5 was missing. So here 6 and 7 were missing. So similarly, here 7, 8, 9, they will be missing. Okay. But so my question is, first, prove that. Oh, yeah, maybe. I'll leave it up to you, because I want you to experiment and actually phrase the right question. So what should be the right question? And one more really difficult question for which we don't have an answer yet is that in how many essentially different ways one can draw n straight lines in the plane. Okay. I hope this question is easy to understand, but I guarantee you that it's very difficult to prove. In fact, it's not. It's very difficult to solve. In fact, we don't have an accurate answer for this question. For example, n is equal to 2, right? So if you have 2 lines, then 2 of them can be parallel or they'll intersect. That's it. There are essentially 2 ways, right? It doesn't matter if I draw this as this or something like this or this. Or I'll consider all these equivalent. Similarly, this, all of these are equivalent. So there are essentially 2 ways. So we have to accurately define what it means to be essentially different, or how do we include the equivalence of lines, arrangement of lines. But given that, if you're able to come up with that formulation, what should be the essentially different way of drawing lines? So for example, 3, we already did, right? So 3 parallel, or you can have this, or this, or this. That's it. Nothing else is possible. Okay. But for 4, you can do it. I think if you have excited enough about this subject, and if you're patient enough, then maybe in a day or 2 you'll be able to do, I think 8, 9, or let's say 10 lines. But if you want to go to 20, you'll really need more persistent efforts. But that's also doable. But again, you can just build a catalog out of it, but that will not answer. But what it will do is that it will help you develop the mathematics. Okay. So with this, I would like to stop because I think I've exceeded an hour. So based on this, we can have a discussion. Okay. Thank you.
Thank you, sir. Thank you for your talk. Now the session is open for the discussion. The participants are requested, if they have any doubt or any question related to the given lecture, so they can freely ask to the resource person. Yes, the questions are welcome from the participants.
Participants can unmute and ask the questions.
Yes, please.
आपण असं समजूयात की गप्पा मारायला वेळ आहे, त्यामुळे या आधीच्या याच्यावरती पण कोणाला बोलायचं असेल या सेशन वरती तरी बोलू शकतो आपण. म्हणूनच मी हे 2 गोष्टी इथे ठेवल्या. आणि हे 4 मुद्दे टॉप मध्ये आले का असाही विचार आपण करू शकतो.
Yes. Okay. If there is no question from the audience, then we come to the last session of today's program. So that is nothing but the vote of thanks. So I request my colleague Ashwini Kai ma'am to
Pimpre sir.
Yes.
Shinde sir नाही बोलणार का?
Sorry. Okay.
I'll just stop presenting.
Okay. So, okay, sir. Sorry, sir. So there is now I invite today's chairperson, Professor Sadashiv Shinde, sir, Vice Principal, Raishi Shahu Mahavidyalaya, Latur, to give his presidential talk. Please, sir.
Thank you, Dr. Nishant. Good afternoon to all of you. Hello, am I audible?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Audible.
First, at the onset, I heartily welcome you all on this auspicious occasion of the Pi Day. The Department of Physics organizes a very popular series, the popular talk, that is how to cut an Uttapam. For this program, the chief guest, Dr. Priyavrat Deshpande sir, our former principal, Dr. Subhash Muttepawar sir, head of the department, Dr. Mahesh Wavre, Dr. Nishant Pimple, Sri Deepak Guge, Srimati Ashwini Kale, all participants from Maharashtra and abroad, professors from mathematics departments from other colleges and universities, and all students. Friends, Today we are celebrating the pi day. The number pi is a mathematical constant. It is the ratio of the circle's circumference to its diameter. It is also referred to as Archimedes constant. Around 250 BC, the Greek mathematician Archimedes created an algorithm to approximate pi with arbitrary accuracy. This symbol was devised by British mathematician William Jones in 1706. It was later popularized by Swiss mathematician Leonhard Euler. Friends, March 14 or 3/14 is celebrated as Pi Day because 3.14 are the first digits of the pi. Pi is actually a part of Egyptian mythology. People in Egypt believed that the pyramids of Giza were built on the principles of pi. The pyramids are phenomenal structures and are one of the 7 wonders of the world. Physicist Laurie Shaw started celebrating 14 March as Pi Day at San Francisco's Explanetarium Science Museum. There he known as the Prince of Pi. The Wales mathematician William Jones, a friend of Sir Isaac Newton, began using the symbol pi in 1706. Friends, the constant pi helps us to understand our universe with greater clarity. Pi is the most important number in the universe. Dr. Deshpande sir enlightened us by highlighting number of issues related to the mathematics. Friends, as per my opinion, the subject mathematics is very important subject at the global level. For your kind information, I would like to say the mathematics starts when a particular individual borns. Means by birth of a particular individual, the mathematics starts. And I will never say the mathematics ends by the death of that individual, but the mathematics remains immortal. My mathematics is the part of the breath, you can say. That's why mathematics is very important to the life of each and every individual. Maths is certainly precise. There are rigid standards clarified by logics, imaginations, curiosity, demonstrative reasonings, learning maths by own experience, inductive aptitude in mathematics, observation, and pattern recognition. As I said, mathematics is the basic subject. As I said, mathematics is the important subject. Several questions can be. Please mute the mic. Mute the mic. Nikita. Mute.
निकिता एलगट के माइक म्यूट करा.
Okay, let us come. Here I was saying that someone gave me 2 digits of one number. When I am putting a symbol of plus in between these two one numbers, the result becomes 2. When I am putting the symbol of multiplication in between these two, the result becomes 11. Instead of 11, we are expecting here 11, but the result becomes 1. And when 1 placed before or after 1, the result actually becomes 11. Why this is happening? Such type of the questions, I am saying that obviously the answers are there for these questions, but we are not getting the answers since our birth. When we are starting our education, mathematics should become the popular subject. As per my opinion, any subject should not be the difficult subject or the simple subject. Certainly this happens. Then why the students are facing the difficulties with the mathematics? As per my opinion, the difficult, whether the subject is difficult or simple, this is related to the teachers. If some teachers are there, say for example, teachers like our respected Muttapam sir, he used to simplify the subject. Means everything is dependent on the teacher. Simple question is there. 1 plus 1 becomes 2. 1 into 1 becomes 1. 1 ahead 1, it becomes 11. Why this is happening? I am not saying this is the question as like the egg earlier or hen earlier. This is the mysterious question. In my opinion, there is no mystery in the mathematics. Mathematics is the simplest subject, and we have to behave in that way. Friends, today is the Pi Day. Our Department of Mathematics is celebrating this event. Every year they are celebrating. That's why I appreciate their efforts. Obviously, they are very much active fellows. In addition to this one, in addition to this event, I must speak about my college, because we are celebrating our Golden Jubilee year this year. Friends, we have started our journey before 50 years. In the language of mathematics, I can say we have started our journey with the 0. Where we are marching? We are marching, our march is towards the N. N we are having. We are not marching towards the zenith. I am not saying we have reached to the zenith. We are marching towards the zenith. Friends, we have started our journey with the go down. When we started our college in the simplest building, that building was named as the go down. We have transformed that go down into the go down of knowledge. And this is not happened in one night. Friends, it is said Rome was not built in one night. In the same way, I can say Rajarshi Shahu Mahavidyalaya is not built in one night. This is the college of merit. This is the source of merit. When our merit started by the year 1981, here since then we are marching towards and towards and towards and towards. In the language of mathematics, what we are doing? Every year we are adding the number before 0, not after 0. We are adding the number before 0. This year, for your kind information, this year about 900 students admitted to the government medical college. About 34 students admitted to the IIT and NIT. About 25 students admitted to the AIMS Medical College. This is the result, and this result is not because of the efforts of one night. This is the result of persistent devotion. This is the result of persistent dedication. This is the result of hard work. This is the result of painstaking efforts. Friends, we did this. That's why we are meritorious. Dr. Deshpande sir, you might have been heard. Here, this is the college of Latur pattern. Whatever the efforts that we have taken since last 50 years. Honorable Vilasrauji Deshmukh, they use the name Latur pattern for the efforts of Rajarshi Shahu Mahavidyalaya Latur. And the Latur pattern became popular not only in Maharashtra, but it became popular in entire India. Now it became the global issue now. Now our students, they are working as the scientists, they are working as professors, they are working as doctors, engineers. N number of students we have produced within the 50 years. And we are here proudly celebrating 50 years, that is Golden Jubilee year this year. Sir, government of Maharashtra here gave a very important, you can say, our institution felicitated by government of Maharashtra. We are the recipient of Best Institution Award by government of Maharashtra. We are the recipients of Best College Award by Parent Institution. Our principal, best principal from Parent Institution. N number of awards we received. Such a kind of the journey We have started before 50 years and we are marching with very proud we are having. Sir, with these few words, friends, with these few words, I used to conclude here my presidential talk. Thank you for giving me an opportunity to preside over this session. Thank you all. Thank you, Dr. Muttepawar sir, Dr. Deshpande sir, and all participants and Department of Mathematics. Thank you once again. Over to you, Dr. Nishant Pimple.
Thank you, sir. Thank you. Thank you, sir. Thank you, sir, for your presidential talk. Now, I would like to call upon my colleague Ashwini Kai ma'am for presenting vote of thanks. Over to you, ma'am.
Good afternoon to all. Myself, Miss Ashwini B. Kare. I am here to express the vote of thanks. Firstly, I wish you all a very happy Pi Day. On the occasion of Pi Day, that is on 14th March, Department of Mathematics, Rajarshi Shahu Mahavidyalaya Autonomous Latur, organized a popular talk on the title, How to Cut an Uttapam to Get the Desired Number of Pieces. I expresses my deep sincere thanks to the Principal Dr. M.H. Gavane sir, Vice Principal and today's Chairperson Professor S.N. Shinde sir, Professor S.M. Muttepawar sir, former Principal of RSML and former Head of Maths Department, spending their precious time and guiding us. I am very thankful to today's speaker, Dr. Priyavrat Deshpande sir, Chennai Mathematics Institute, Chennai, for delivering such a nice and conceptual lecture to enlighten our students. I am very thankful to Dr. M.S. Vavre sir, Mr. N.S. Pimple sir, Mr. D.M. Guge sir for organizing this popular talk. I also thanks to all student participants, teacher participants from other universities such as BAMU, etc. and all mathematics lovers. Thank you to all. Thank you, sir, for giving me an opportunity to express my vote of thanks. Thank you.
Thank you, sir. Thank you, ma'am.
Thank you.
Thank you, sir. Thank you, today's resource person. Deshpande sir. Thank you.
Muttepawar sir,
thank you.
Thank you,
My teacher.
Thank you all. Thank you
Muttepawar
all.
sir. Thank you, sir.
Thank you.
Yes, thank you. Okay.
Thank you, sir. So, with the permission of the chairperson for today's, so I come to the conclusion that today's this session is over. Thank you. Thank you, one and all.
Thank you. Thank you.
Vavre sir, over to you.
Oh.
Thank you.